Hello everyone, welcome to review of units 1 through 4 and 6 of AICE Physics. So in this two-part thingamajig, we're gonna go over basically FRQ questions mainly. But yeah, so there's already an MCQ one that's already posted. So if you want to practice MCQ questions, you can go there and watch it. Otherwise, we're just gonna go ahead and do these FRQ problems. So number 1. Length, mass, and temperature are all SI units. State two other SI base units. So one SI unit that should automatically come to mind is time, which is has a unit of seconds or S. The second one is a little bit more unintuitive. Usually you know it or you don't. So in this case, it's going to be current, which is represented by amps. Yeah, this is kind of one of the problems. Later, there's a question that's using these amps. This is actually part of a test that I took, and during the test, I didn't actually know what the second one was until like I did the second problem. And then I just used the second problem to answer the first problem. So, yeah. Anyway, back to B. The acceleration of freefall G may be determined but from an oscillating pendulum using the equation of this, where L is the length of the pendulum and T is the period of oscillation. In experiment, the measured values for an oscillating pendulum are L is equal to 1.5 m, and then T is equal to 2.4 s. Calculate the acceleration of freefall G. So they give us an equation and they give us values, so we can simply just plug in the values for each one. So it's going to be 4 pi squared times L, which is 1.5, divided by T squared, which is 2.48 squared. And then you just use your calculator to do this. And then you get 9.628, which is kind of near to 9.61, but you know, there's uncertainty here, so not necessarily correct. For FRQ questions, you should always remember to round to 2 sig figs, unless otherwise stated. Even though it says 3, but just do 2, just cause. Anyway, determine the percentage uncertainty in G. Okay, so let's look at our equation for G. So these are our two values that contribute to percentage uncertainty. So in this case, the L contributes plus or minus 2%, and then the T contributes an additional 3%. But since it's squared, we count this twice. And then we just have to add these two up. So you get 2 plus 2 times 3, which is equal to 8. So it's 8%. I should say that when you're multiplying / dividing, you have to be using percentage uncertainty. And then when you're calculating percentage uncertainty in total, you have to add them. So yeah. Use your answers in BI and B2 to determine the absolute uncertainty of the calculated value G. So we take G, right? And then our absolute uncertainty is just going to be converting our percentage uncertainty into absolute uncertainty. So we multiply this by 0.08, which is 8 in percentage form. And then you get 0.768 or 0.77. Number 2. Use an expression for work done in terms of force to show that SI base units of energy are kg m2 s negative 2. Okay, so recall that work is equal to force times distance. So that means that work is equal to ma, because F is equal to ma, Newton's second law, multiplied by S. Now let's try, we actually know that these are pretty common units, so we can actually convert everything into like the unit form, right? Substitute the units. So mass is going to be kg, acceleration is going to be meters per second squared, and then distance or displacement is m. And if you do this calculation, you get that joules is equal to kg m squared per second squared. Okay, BI. The energy E stored in an electrical component is given by E equals Q squared over 2C, where Q is a product of current and time, and C is a constant. Use this equation and the information in A to determine the SI base units of C. So we're trying to find C, right? So we take this joules, right? Let's try and substitute our units in. So we have Q squared over 2C. So it becomes joules is equal to, they give us that it's current and time. So it's going to be ending up going to be amps multiplied by seconds, which is time, squared over 2C. So let's actually try and solve for C. So we multiply by C and divide by joules. So we flip-flop it. So we get amps S squared, I distributed the power, over joules. And in fact, we actually calculated joules up in question A. So we can substitute this further. Kg m squared s negative 2. And it turns out that we can simplify this equation to get amp squared kg negative 1 meters negative 2 and then seconds to the 4. (3a). Figure 2.1 shows the velocity time graph for an object moving in a straight line. Determine an expression in terms of UVT for the area under the graph. So if you don't know this, you should learn how to derive this because this is pretty useful. If you forget it, you can derive it like on the exam and nobody will like hate you. But this is using like an intuitive approach. So we're looking for the area under the graph. If you've taken calc, this is kind of like a trapezoidal rule, right? So we're looking for this area, but these are right angles. So it turns out this is actually a trapezoid with bases u, v, and a height with t. So it's a trapezoid on its side, basically. And then the area of a trapezoid is just simply u plus v over 2 multiplied by t. And that is our answer. State the name of the quantity represented by the area on the graph. In this case, it's just displacement. This is a kind of like a definition question. You either know it or you don't. A ball is kicked with velocity 15 meters per second at an angle of 60 degrees to the horizontal ground. The ball then strikes the vertical wall at an instant when the path of the ball becomes horizontal, as shown in figure 2.2. Assume that air resistance is negligible. So we have our little path here, and then, yeah. It's looking pretty good. Okay. By considering the vertical motion of the ball, calculate the time it takes to reach the wall. So we're given that when it strikes the vertical wall, the path of the ball becomes horizontal. This means that the y component, how do I say this? V of y is equal to 0. So we have our initial, right? And then we have our final. This is 0, and our initial is going to be 15 multiplied by sine 30. No, sine 60, sorry. This is because we take the initial velocity coming from like the ball and when it's kicked, right? So this is the initial, and then the final is over here. So it turns out this is going to be around 13. It's 12.99, but you can just do 13. 13 meters per second and 0 meters per second. So another thing we can deduce is that our acceleration. So our acceleration in this case is going to be negative 0.81 because it's decelerating, and this is just gravity. Yeah. So using these three, we can try and solve for the fourth variable of time. So I'm pretty sure you use this Suvat equation, v equals u plus at. This is because I kind of just think about it like this. So this is our initial and this is our final. And then if you're decelerating, it's based on the time, right? So initial, final, acceleration, and then time. So we can just plug these in. So 13 plus negative 9.81 t is equal to 0. Move the t variable to the other side. And then we divide to get 1.3. Explain why the horizontal component of the velocity of the ball remains constant as it moves to the wall. Well, the horizontal component is going to be remaining constant because the air resistance is negligible. Sorry. So air resistance is negligible. Thus, that means that no resultant force is acting on a ball. This means that acceleration is 0, and thus our velocity is constant. Show that the ball strikes the wall with a horizontal velocity of 7.5 meters per second. So this is kind of clever. So if you look at the previous part, each part is kind of related to each other. So we are given that the horizontal component of the velocity remains constant. This means that the horizontal velocity of the x is equal to the final velocity of x. So we can just calculate the initial one, which is based on this triangle here, right? The 15, y, and then x. So this is going to be 15 cosine of 60 is equal to v of x. And if you calculate this out, this is 7.5 meters per second, which is to be shown. C. The mass of the ball MB is 0.4 kg. It is in contact with the wall for a time of 0.12 seconds and rebounds horizontally with a speed of 4.3 meters per second. Use the information from B3 to calculate the change in momentum of the ball due to the collision. Okay, so change in momentum is going to be mv minus mu, where mv is the final velocity and then u is the initial velocity. So, and you have to account direction for this. So we're going to say that this is going to be negative direction. Like towards the wall is going to be a negative direction. And it's heading here at a speed of 7.5 meters per second. So initial and then final is going to be a ball going this way. And they give us the final velocity of 4.3 meters per second. So if we calculate this out, we get mv, so 0.40 multiplied by this one right here, the final velocity, minus 0.40 multiplied by the negative direction of this, negative 7.5. So then this is going to be equal to 4.72, which is going to be 4.7. Calculate the magnitude of the average force exerted on a ball by the wall. So force is equal to the change in momentum or the change in time. So this is a formula that is pretty commonly used. So make sure you are familiar with this. So F in this case is going to be the change in momentum, 4.7, or the change in time, which is 0.12. Which is going to be 39.1667, but it's only 2 sig fixed, so it's going to be 39 newtons.